Good morning. So today we're gonna still be talking about squares and cubes a little bit, or at least staying in the same neighborhood. But we're taking our discussion a little bit more geometry based, and today will hopefully be a little bit just more like discovery stuff like that. Normally there'd be some hands-on discovery things we can do with like tiles and paper and stuff. So I'm gonna show you a couple of videos online today. Hopefully they will be a little bit clear as to what they're showing. It might be a bit advanced into the details that's going on, but hopefully visually you can see what's going on. And we're going to look at right triangles. So we're still going to talk about squares and square roots, but the side lengths of right triangles in particular have a special connection to square roots and squares. So we're going to start by looking at a couple of vocabulary words. The first of them is going to be the lengths of the side lengths of a right triangle. So it turns out, so basically when you have a right triangle, so I'm trying to make this shape nice and clear. So when you have the side lengths of a right triangle, they are called the legs. Alright, so the legs refer to the sides that are attached to the right angle. Okay, so the legs are the sides that are attached to the right angle, and they are also the two shorter sides. So the leg is attached to the right angle. There's two of them, and they are the shorter sides. And the long side, the longest side of the right triangle, is called the hypotenuse. So the hypotenuse is the name of the longest side of the triangle, and it is the side opposite the right angle. Hold on. A bit smaller, so it all stays on one page. So the hypotenuse is opposite the right angle, and it is the longest side. All right, and it looks like you can tell it's the longest side. It clearly looks longer than the other sides. And the hypotenuse is always opposite the right angle. It's the longest side of the triangle. And we're going to learn about a special relationship that the legs have to the hypotenuse in a right triangle, and it relates to squares and roots. So we're going to look at a couple of videos to explore that relationship now. So we're going to just go through a couple parts of a couple YouTube videos because they show a couple of pretty good visual demonstrations. This one goes into a little bit of the history. I'll warn you, some of the language is a bit high. She talks a bit fast. So if you want to see it again, I recommend going through and watching the YouTube video at like a half speed or 2/3 speed. But I'm going to try to pause it and just sort of draw your attention to the important things, okay? So we're just going to watch this for a couple minutes.
What do Euclid, 12-year-old Einstein, and American President James Garfield have in common? They all came up with elegant proofs for the famous Pythagorean theorem, the rule that says for a right triangle, the square of one side plus the square of the other side is equal to the square of the hypotenuse.
Okay, so right there we have the A and the B are the legs, and the squares, they're building squares off those side lengths. And if you add the areas of the squares A and B, you'd get the area of squares C. That's what we're going to try to prove. And they're going to try to show it a couple different ways. Even if you only get one of them, that's fine. All right, just try to absorb what they're saying, okay?
In other words, a squared plus b squared equals c squared.
You're going to see that equation a lot, so just keep that equation in your mind. A squared plus b squared equals c squared.
This statement is one of the most fundamental rules of geometry and the basis for practical applications like constructing stable buildings and triangulating GPS coordinates. The theorem is named for Pythagoras, a Greek philosopher and mathematician in the 6th century BC, but it was known more than 1,000 years earlier. A Babylonian tablet from around 1800 BC lists 15 sets of numbers that satisfy.
So these are all just examples of numbers where that works. If you try them, if you do 120 squared plus 119 squared, you will get 169 squared, and that'll work for all of these numbers, and there's many more. Actually, there's deceptively few that work, but we'll talk about that later. All right? The moral of the story is they've known about this for a very long time.
By the theorem. Some historians speculate that ancient Egyptian surveyors used one such set of numbers, 3, 4, 5, to make square corners.
3, 4, and 5 is probably the most famous of the Pythagorean problems. Those side lengths of a right triangle will come up a lot.
The theory is that surveyors could stretch a knotted rope with 12 equal segments to form a triangle with sides of length 3, 4, and 5. According to the converse of the Pythagorean theorem, that has to make a right triangle, and therefore a square corner. And the earliest known Indian mathematical texts, written between 800 and 600 BC, state that a rope stretched across the diagonal of a square produces a square twice as large as the original one. That relation...
It's pretty cool. That is actually very true. If you use the diagonal as a side length, this C square is actually twice as big as this one, the A square. Pretty cool.
Relationship can be derived from the Pythagorean theorem. But how do we know that the theorem is true for every right triangle on a flat surface, not just the ones these mathematicians and surveyors knew about? Because we can prove it. Proofs use existing mathematical rules and logic to demonstrate that a theorem must hold true all the time. One classic proof, often attributed to Pythagoras himself, uses a strategy called proof by rearrangement. Take 4 identical right triangles.
So you're going to try to see where these 4 triangles fit into the shape. They're going to take these 4 triangles and, like they said, rearrange them. They're going to move them around and show that 2 things actually are the same. They just are put together differently. So we'll definitely take our focus here and maybe watch this part, especially on half speed at your own if you can. Can I put on half speed here, actually? Playback speed. Let's try 0.75 speed first. All right.
With side lengths A and B and hypotenuse length C. Arrange them so that their hypotenuses form a tilted square. The area of that square is C squared. Now...
Okay, so we arranged it one way. And that way we arranged it shows this white diagonal square. And that square, the side length is the hypotenuse. So that side length of that square is C. So it's a C by C squared. So this area of the square is C squared. And keep in mind, there is a big square out here, and that big square is just, it's the C squared, but it's also these 4 identical triangles. So there's 4 triangles and a C squared. All right, so let's look at how they rearranged this to make a new shape that's kind of the same general big square, but with the different pieces inside.
I'll rearrange the triangles into 2 rectangles, leaving smaller squares on either side.
So now we've rearranged it, so now there's 2 rectangles made up of the triangles, and 2 rectangles here made up of the triangles. Now look at how the white section has now been sort of changed. The section that was not the original triangles is now 2 squares. It's a B by B square, which is going to be B squared, and an A by A squared, which is going to be A squared.
The areas of those squares are A squared and B squared. Here's the key. The total area of the figure didn't change, and the areas of the triangles didn't change. So the empty space in one, C squared, must be equal to the empty space in the other, A squared plus B squared.
There's a lot of different ways you can do proofs similar to this, but hopefully that one made sense in watching it, and that just the blank space, the way it got shifted around, keeps the areas of the squares the same, so that a squared and that b squared end up totaling the same c squared diagonal square from the first one. Alright, so I think that's where we're going to stop in this first video. The next couple get a little confusing and weird. The next one goes into similar triangles, which you can watch, which relates to what we talked at the beginning of the year. But honestly, it confused me the first time going through it, so I'm not really sure I want to show that one. So we'll pick up with a different one next. This is like a little water demo. It's like someone's simple like science fair project or something. I've loved this video since I saw it. It's very creative, and basically this girl's got a display with a right triangle, and she drew squares, or made squares, off of each of the legs, the shorter sides, and a square off the hypotenuse. And they're squares, they all have that side length of the hypotenuse. And the two legs are filled with water. I want you just to watch and see what's going to happen with all that water when she rotates the triangle. So the water from the two legs exactly filled the water from the hypotenuse square, meaning that the squares off of each of the legs contain the same total capacity as the third square off the hypotenuse. Alright, and she's going to turn it back the other way, I think, and that's going to refill the two legs, which you might as well watch. Pretty cool, huh? Okay, so there's that one, and I think we have one more video to watch. Okay, this one. I'm going to figure out what part of this video I actually want to watch and then continue in just a second. The last one is actually similar to the proof we saw at first, the proof by rearrangement, but it's going to be a different kind of rearranging. And that we're taking the right triangle with the boxes built off of it and doing something else with them. So I'm going to skip ahead to the part where they actually do the rearranging, because I don't get distracted by all the lines they draw. So I'm going to skip ahead 1 minute. You can watch the rest of it on your own if you can find this video. The title's right there. I'm going to skip ahead to 108. I'm going to see how they partition or break apart the square of a squared. And now what they're going to do is they're going to try to fit in the a squared and the b squared all down into the big c squared and show you that the two leg squares are the same as the hypotenuse square. Sorry about the music. So that's basically the gist of it. They took the four pieces of the a squared and they put it down here and arranged it so that the b squared could fit in nicely with no missing pieces. So it shows us that the a squared plus the b squared equals the c squared. Alright, so hopefully that made it a little bit okay, I see where that's coming from now. Even if you were like, I could never redo that on my own, or I could never, sorry for all the home remodel suggested videos, that's what I'm doing right now. Yeah, so you can check out any of these videos again if you want to. I'll post the links. You do not have to watch them, obviously. That is not a requirement. I tried to show you just the best parts of the video so that you could see what was going on here. Alright, so that made it easy to see that in a right triangle with the legs A and B, the squares of the side lengths, or the squares of the legs, added together, will exactly equal the square of the hypotenuse. Alright, and we'll get more into dealing with this and doing math with this later. Hopefully this isn't too bad of a Friday lesson. Hopefully it was, hopefully it wasn't too bad. Alright, enjoy your day, and don't forget to fill out that form. The form today will be, I haven't decided if it's going to be like 2 or 3 points, or like, it's going to be collected only, but there's only a few questions on it. Alright, it's collected only, so don't worry about a pass-fail today. Just get it done so I can mark it as done. Thank you.